Welcome in. So let's prove the quotient rule for derivatives. It's one of the easier proofs that we actually have. Now, I am going to utilize the product rule for derivatives, and I have proved that one. I'll put it up above there if you've forgotten about the product rule. And also, I'm going to use the chain rule, okay, so for composite functions. And that one is one of the harder ones to prove. I'll put up a link to the chain rule up above there if you need a refresher. Now, if we have our product rule, so I'm going to just kind of do a deja vu for you. Now, if I had a function, and let's call this function now g of x, and this function was made up of two functions, let's say f1 of x and then multiplied by f2 of x, so it's a product of two functions, then we know by the product rule that the actual derivative becomes f1. I'm going to just drop this just so that I'm not writing the x all the time. So it is f1 in terms of the derivative multiplied by just f2, so we don't take the derivative there, plus the actual f1 stays alone, and then you multiply by the derivative of f2. So that is the derivative of g, and that is utilizing the product rule. So that's the number one thing. Now, the other thing that I'm going to use here is the quotient rule, but the quotient rule is going to be rather simple in here because I'm going to transition this denominator and bring it up to the numerator. So I'll tell you when that comes about. So this is what I really want to be able to use in order to prove my quotient rule. And you'll see that the derivative of the actual original right here is, so let me copy this, bring it down for you. So the derivative, if you wanted to know what it is in terms of the quotient rule, it would have been equal to the derivative of the numerator as a function multiplied by just the denominator, and it is being subtracted from the numerator, not the derivative, just the actual numerator itself, multiplied by the derivative of the denominator. And all of this is going to be divided by the denominator squared. Maybe I should write it in full, dx, so this entire thing squared. That is the quotient rule. I don't like remembering the quotient rule. It's not bad when you're using it often enough, but I actually just simply will remember the actual product rule that we have right here so that I don't have to remember the quotient rule as much. And you'll see why, because I'm going to do the proof to show that this is actually true with respect to the quotient rule. So let's begin. If I'm beginning, then what I'm going to do first, okay, so with respect to our proof, is the following. So let's transition. So I'm going to rewrite f at x is equal to the numerator multiplied by the denominator, but of course now the denominator is going to be to the -1 because it is right here at the bottom. So these are equivalent. So if you know your exponent laws or rules, okay, then you know that this is true. Now, once I have this, then I can now apply the product rule because of the fact that I have two functions here. I have this function and I have this function. So I'm going to do that. So first, okay, so I will take this and break it down. So in terms of its derivative right here, what we're going to get is, by the product rule, this just simply is the derivative of n. And I'm going to drop the x for the moment. I just don't want to complicate things for myself. And it's going to be multiplied by d, okay, in terms of the actual second item right here, plus Now it's going to be just n on its own multiplied by the derivative of all of this. And here is where I'm going to be using the chain rule. So the chain rule with respect to an actual exponent is rather simple. So we just simply take and we bring down the exponent. So that's going to be -1 multiplied by dx. Maybe I'll just keep the d as I said. This is going to be to the -2 because we're subtracting 1 from here. And it's going to be multiplied by the derivative of whatever is inside of here, which is just the d on its own. That comes from the chain rule. And again, if you've forgotten about the chain rule, I'll put up a link up above there for you if necessary. So now with this, if you take all of this, then we're pretty much almost done. We just have to massage this. So what does this look like? Well, this looks like n all over d. So I'm going to bring this down. Now this -1, so this is going to be subtracted. And notice this is going to be n right here. And I'm going to multiply it by this d and the derivative of that. And all of this is going to come down. I'm going to bring it down to the denominator. So that's going to be d squared. Now, if you want a common denominator in between both, then what you would have to do is you would have to multiply this side by d over d so that you have d squared. And notice what you'll get. You'll get n prime, which is the derivative of n, multiplied by d minus n multiplied by the derivative of d all over d squared. And now you can fill in with the actual variable x and you will get exactly what you were looking for. So there you have it. That is the proof of the quotient rule for us. There we go. This is what it would be. And now we just have to apply it whenever we want. But that is the actual proof that you have utilizing the product rule and the chain rule as well. All right, thanks for watching. We'll see you in a future video. Bye, everybody.